the apparently serendipitous, accidental discovery of the bell curve by the Moivre in 1733 was to have deep and portentous consequences. As is the case of endeavour typically in mathematics and in science, great and abiding pathways arise from very small beginnings. After the Moivre's initial discovery in 1733, it took 80 years before the next development, before Pierre-Simon, Marquis de Laplace, extended the Moivre's analysis for a fair coin to bent coins. And from the early part of the 19th century onwards, the developments proceeded apace and gathering speed as the century moved on. By the end of the 19th century and by the early part of the 20th century, it had become apparent that that apparently accidental discovery of the Moivre was really fundamental, that the bell curve arose everywhere, and it was not an accident. This led ultimately to that basic principle in probability, perhaps the preeminent principle in probability, that is called the central limit theorem. Let me give you a version of the theorem, and unapologetically, without any proofs at this point, a version that is very comprehensive and already takes into account a large application domain. So, to begin, we're going to start with a random sample, as always. It's an honest sample. We're thinking of repeated independent trials. There's an underlying distribution which spits out numbers, and we're going to draw independently from that distribution. X is a generic example of an outcome of this experiment, and we perform independent copies of X, X1, X2, X3, Xn, and so forth. A setting of repeated independent trials. Suppose additionally that the underlying distribution or chance law has an expectation, a probabilistic center of mass, mu, and a variance, an expected squared deviation from the center of sigma squared. Starting with this, we promptly form a sequence of partial sums. Sn, as always now, is a sum of the first n x's. Now, we want to look at this as n becomes larger and larger and larger. We're going to look at the sequence of partial sums Sn. And you should draw freely from your experience with the binomial. Now, the distribution of Sn can be quite complex. It's inherited from the underlying distribution of the x's. But in general, it's going to have a really complex form. There is no hope in general to find a closed form solution for what the chance law of Sn is going to look like. But if we look at it asymptotically, as n becomes large, well, then we should look at it with a proper centering and a proper scale. Our experience again with the binomial tells us that we should standardize, and for every n, form a new variable, Sn star, properly centered at zero expectation by subtracting from Sn n times mu. Remember, additivity rides to the fore here. That centers the distribution at the origin, and then putting in place a common scale by dividing by the spread or the standard deviation of Sn. Additivity again tells us that variance of Sn is n times sigma squared, so the standard deviation is the square root of n times sigma. We now have a standardized variable, properly centered at the origin and viewed in the proper scale. We're now looking at, if you like, a dimensionless variable. In the context of the binomial, we realize that this Sn star was governed essentially by a normal distribution, essentially by the bell curve. And remarkably, almost 4 centuries after the Moivre, we find that this is true quite generally. The probability that a properly centered variable, a sum variable viewed in the proper scale, lies between any given range you choose, between, say, an A and a B, is given approximately by the area under the bell curve between A to B, no matter what the underlying distribution or chance law was. This is remarkable. This explains why the bell curve is so ubiquitous in theory and in application. Sums are endemic in science, in engineering, in mathematics, in sociology. And because sums are so prevalent, if we have reason to believe that the perturbations making up the summands are independent, then we should expect that a suitably centered and scaled version of the sum will behave like a normal law. This is remarkable. This theorem is perhaps the central theorem, the most important and fundamental theorem in all of chance. And we can already get a glimmer of why it is so portentous, why it is so weighty. It applies in all kinds of circumstances, regardless of the underlying starting distribution. This theorem has the role of an éminence grise, the grey eminence, with an aside reference to the Cardinal Richelieu. It informs essentially the entire theory. And it's because of this remarkable fact that the bell curve crops up again and again and again, essentially whatever the underlying chance laws. Now, as the 20th century progressed, this result was strengthened and further generalized, and it continues to be generalized today into varieties of circumstances, settings where the variables are drawn from, say, different chance laws but are still independent, settings where the variables have values in more than one dimension. In other words, we're adding random vectors, settings where the variables are not independent but almost so, settings where there's only a weak dependency across the variables. The bell curve keeps cropping up again and again and again. An understanding of these circumstances then leads to other limit laws where, for example, the variables have dependencies, or perhaps the variables don't have variance, or some perhaps where the variables don't even have expectation. This accidental discovery of the Moivre from 1733 had fruits far beyond what could have been anticipated at that time. This has informed essentially all of modern probability, and as we shall see, has informed application domains in a huge spread, a huge palette of possibilities. Of course, the further we go along with these results, and the more we try to tweak out of this, the more it is clear that we're going to need mathematical dexterity. And so, yes, the later reaches of this kind of result are prodigiously difficult sometimes. They require a lot of mathematical background. But at the end of it all, the result itself is startling in its simplicity. And perhaps, again, because we are dealing with a political age, a slogan to summarize the essential features of this mathematical result is appropriate. The sum of independent perturbations follows a normal law.